small part of a very large American base. The Danes have not been cooperative in allowing Oscar to be moved to higher elevation. That's been several years. Once Trump gets the army marching in there, they may be able to
There's no magic word.
Well, you're always welcome to the data. I mean, it's big enough, it could be a whole bit of red.
Which telescope is this?
Okay, welcome everyone on a very dreary day. We all made it. Fewer than we had hoped. Some people could not make it, but as a result, we will have only 3 presentations today. We don't have the ITC colloquium this month because there are too many talks. So we were asked not to schedule the ITC colloquium. So that's on purpose. It's not because people quit. And we will start the colloquium once again in March. So that's just temporary. Indeed, we have a lot of talks. There was a colloquium today in the morning. Some of you may have attended. So we will hear first from Guido Risalti from the Universita di Firenze, from Firenze, Italy. And he will tell us about quasars as standard candles. And then we'll hear from Jesse Hahn about the paper that he posted on the archive. Where is Jesse? Oh, behind. Posted on the archive, so we had a preview. But for those who haven't seen it, it will be about hypervelocity stars as coming from a massive black hole in the Large Magellanic Cloud. So usually it's thought to have originated from the center of our galaxy, but Jesse found evidence in the latest data for some of them coming from the Magellanic Cloud. We'll hear more about it. And then from Tony Stark, finally will tell us about Triaxial models of galaxies. So Guido, take it away.
Okay, hello everybody. I'm not sure whether I
Need the microphone? Yes,
yeah,
I do. Okay, good. So it's recorded.
Great. Okay, yeah. So what I'm going to talk today is about our attempt to use the quasars as high redshift standard candles. So where are we in this ambitious project? Just a very brief introduction. Our idea is to estimate quasar distances from the nonlinear relation between the X-ray luminosity and the UV luminosity in quasars. The X-ray luminosity, which is believed to originate from a hot cloud, which is usually called the corona, somewhere around the accretion disk, while the accretion disk is the main source of the quasar luminosity peaking in the UV. And there is a lot of complexity in the observed emission in both X-rays and in the UV. And however, spectrally, it seems that there is little redshift and luminosity evolution in the main quasar properties, both in the X-rays and the UV. However, when we compare the X-ray and UV luminosity, we find that there is a linear relation in log units, but the slope is not 1, which means that in physical units it's a non-linear relation. And so from this non-linear relation, in an obvious way, it's possible to derive a distance and then use it as a cosmological standard candle. Well, just jumping to a possible happy ending of this story, okay, here I show what we can do with the quasars that we have now, so with reliable measurements both in the UV and the X-rays. And here we have a Hubble diagram with the supernovae as the green points, and the red points are what is derived from quasars, and the inner plot is just a zoom. Well, it was supposed to be a zoom, sorry, it's the same one. Well, basically, there was a problem. Yeah, the next one is okay, anyway. Just to show that there is a very good match with supernovae in the common redshift range, but there is a significant deviation at redshift higher than 2 with respect to the lambda CDM model. And so this in itself will be a great result, no? Where is my Nobel Prize for that, no? However, it's not that simple, because what I'm showing here are the averages obtained with quasars in small redshift beams. But if I add to this plot, and so I also correct the inner plot, I add the individual sources that I used to make this plot, I obtain this one, and the yellow points are the individual quasars. So the averages look pretty good, but can we be sure that there is no systematic effect in such a large dispersion in individual quasars? In order to be reliable cosmological standard candles, we need a precision of the order of a few, at the percent level, okay? So, I mean, we have a hard work in checking and convincing ourselves and the others that there is no hidden systematics in this plot. And here you see that the zoom this time is correct. So what are the main problems? The main problems are more or less what I list here. First of all, is a physical question. Is this relation constant with redshift? Is it redshift independent? Because if there is a physical redshift evolution, of course, this would affect the estimate of the distance estimate. And actually, we don't have a physical model to explain this relation. And then, are there selection effects in the sample? And are there also systematic effects in the flux measurement? Say, if I have a dust extinction which is redshift dependent, somehow that would affect the shape of the Hubble diagram, and so on. So in order to try and discuss all these points, well, we can do several steps. The first one, I already shown it. We can compare what we find at low redshift when we have supernovae to compare with, and this test is okay. We can also study the X-ray to UV relation in small redshift beams and see whether the slope of the relation evolve with redshift, and it doesn't. It is constant at all redshifts. Okay, so this is not yet a proof that there is no absolute normalization variations with redshift, but there is nothing like that up to redshift 1.52, and also the slope remains the same at higher redshift. So there should be something very strange happening at redshift higher than 1.5, changing the absolute calibration of the relation without affecting its slope. Okay. Then what we can do in order to check for systematics is to do a complete spectroscopic analysis, which is a very long work, of both the X-ray and the UV spectra. This is just examples of what we did in the X-rays and in the UV. All our objects have SDSS optical UV spectra and either XMM or Chandra X-ray spectra. And using this data, what we can do is we can investigate the spectral properties of our sample in different beams of black hole mass, luminosity, redshifts, to look for any evolution of the spectral properties, which maybe could be a hint of something happening in our sample. And actually what we find is there is nothing like that. Okay, our sample is since selected in a homogeneous way in this respect. So what we see is that the average spectral properties remain the same at all redshifts, and they do not depend, for example, on black hole mass or other physical parameters. So it seems that we are doing a fair comparison at different redshifts. And another nice thing is that when we try to just select the best observations, okay? So not any selection based on physics, but just on the quality of the observations, especially in X-rays. And so we reduce our sample from a few thousands to, say, 100. So not good for cosmology, but very good to check the physics of the relation. Well, we see that the dispersion of the relation drops, and it goes down to a level of 0.1 dex, which is quite tight, much tighter than the one that I've shown you before for the whole sample. And I don't have time to show you details on this last point, but we can try and analyze this remaining intrinsic dispersion, and it's easy to convince ourselves that there is no room for much intrinsic dispersion of this relation, because this relation here must also account for variability, because X-ray and UV observations are not related to each other, and also to disk inclination. If we believe that the X-ray emission is more or less isotropic, instead the UV emission is not, the inclination of the disk should be seen here as a dispersion of this relation. So accounting for these effects, there is nothing left for a physical dispersion. So it seems, and so I jump to the conclusions, it seems that there is a universal, very tight relation between the let's say, corona emission and the disk emission in quasars. And this is, I think, an important result in itself for the physics of quasars, because it's telling us something fundamental about quasars, and it goes in the direction of, let's say, simplifying somehow our view of quasars. Okay, there is a lot. We know that quasars are very diverse. There is a very heterogeneous population, but when we look carefully at the continuum emission, I mean, there are remarkable similarities. And however, this statement about the physics, I think, is rock solid today, because even if there were I mean, a few percent systematic effects remaining here, from the physical point of view, you know, this is a strong statement. No? Even if I'm wrong by 5%, okay, it's still true that physically there is this universal mechanism. But what about cosmology? Because for cosmology, we have to go down to the 1% precision. And so I think I have shown you that there are several reasons to believe that you know, the effect that we see is real, and there is no reason to believe that there is a relation, an evolution altering the relation that we are using to estimate distances, but well, it's ongoing work to try and reduce the dispersion and further check for all the possible systematics. And I'll also give a high energy lunch talk where I will focus more on some aspects on these things. So thank you very much for your attention.
The assumption here is that the emission is isotropic, but in principle, if the collimation, for example, depends on redshift, there could be many other things that could be a function of redshift that have nothing to do with the spectral slope, like change the relation in a way that would bias it. How do we know that there is no redshift evolution in those other things, like orientation angle, viewing angle?
Yeah, okay, so this is, of course, the question, right? Because that's exactly what we have to solve to make it reliable. And so, of course, we tried hard to think about all the possible effects and to check. For example, for the orientation, this has been already done, and unless there is some physical thing which we completely ignore for what we expect, because there is, of course, an effect. Because since we are always flux limited, going to higher redshift, we select more face-on objects, naturally. This has been considered, taken into account, and it cannot explain, it can explain just a little bit of what we see in terms of the deviation from, say, in the Hubble diagram. So that's you know, in this particular example, we already checked, and it seems not to be the case. Of course, the worry is that there is something which we haven't thought about yet. For example, dust reddening is another very subtle effect which may be very bad for this kind of analysis. We did a careful study about this, and we concluded that it's not possible that this is due to, you know, dust extinction effects. And another one, more physical, is a possible dependence with the Eddington ratio. That's again, we are still working on that. That's subtle. I have now, it's a long thing. Maybe I have to keep my answer short, but we are working on that. I think we are safe regarding that, but it's not so obvious because, you know, we really need to carefully check for these things. Yeah.
Yes, please.
Maybe it's a little question aside of your cosmological implication, but have you ever seen any dependence on the relation that you're presenting UV versus LX on the fact whether the object is radio quiet or radio loud?
Okay, sure. Thank you for the question. There is actually, okay, and just to be safe, we remove all the radio loud objects from our analysis. And if we try and do the same with radio loud, we find something very similar but shifted in calibration. Okay, and so it's, I mean, at best of our knowledge, free from radio loud sources. Yeah.
Okay. There are no more questions. Let's thank Guido again.
All right, cool. Should I go ahead and start?
Except it doesn't show anything.
It shows.
Oh, okay.
Hey everyone, I'm Jesse Hine. I've been here for a few years. And this is my last year as a graduate student at the CFA. So, wahoo wah. How would you find a black hole? You could ask the EHT to observe it, but that only works for a very small number of black holes, right? So some people look for X-ray emission. This is Dali's best impression at an X-ray photon. Some people look at it in radio, right? That's the EHT image itself as well. But today I want to talk about a third kind of emission from a supermassive black hole called hypervelocity stars. It's not an emission of the usual sort, but let me convince you that it actually is a detector of a supermassive black hole. So what are these things? All right, so let's start in the top left corner. We have a nice binary system. Most stars, if you went to Kevin's talk yesterday, most stars are in binary systems, including those that are about to go very close to the supermassive black hole, shown as a supermassive black hole in the plot. So once this binary reaches a tidal radius where the binary itself cannot contain itself, and in fact it is ripped apart by the black hole, one of the stars can get captured by the central massive black hole, and the other one is flung out into infinity at a very, very high speed. And this remaining star, the one that gets launched, is what we call a hypervelocity star, or an HVS. The existence of these kinds of stars have been long around, right? As early as Jack Hill's in 1988, the prediction that some of these stars should be produced in our galactic center from Sagittarius A star has been around for a long time. So let's just read this really quick, right? A Newtonian encounter between a tightly bound orbit, so a binary, and a million solar mass black hole can produce an event where one binary is captured to the black hole and the other one is ejected at a very large number, and the discovery of even one of these stars would be compelling evidence for a massive black hole in our galactic center. Of course, as these things go, it took a while for the first observational confirmation of such a star. So on the x-axis is year, and the y-axis is the number of papers on ADS that has hypervelocity stars in them. There's one at Hills, 1988. There's another around 2000. But then our own Warren Brown here at the CFA discovered the first known hypervelocity star. And since then, a floodgate opened. A lot more observational searches have ensued for these hypervelocity stars, and papers, so forth as well. But among these searches, still the most successful one was the one conducted by Warren here at the CFA. And it is curiously named the Hypervelocity Star Survey, or the HVS survey. So to save you a decade of work, here's a result. On the left panel is the galactic coordinates of where these stars live at present day in our galaxy. So x-axis is where you're looking into the galaxy, 0.0 is the galactic center. And the right panel is the radius from the galactic center and also the galactocentric radial velocity. And then, of course, the blue dashed line is the escape velocity of the galaxy at that radius. So what Warren did, along with his collaborators, were to target stars that are young, massive, blue main sequence stars out in the halo. And these don't usually go well together, right? Because the halo is old, there's not much star formation, if any. So why are these young, massive, blue stars living out there? Well, because they were ejected by probably the Hills mechanism. So among this thousands of stars that he surveyed, they found 21 stars that are consistent with being unbound from the galaxy, moving at speeds that were predicted by the Hills mechanism. Lovely. But there's this curious feature on the sky where about half the sample of the entire survey lies in 5% of the footprint. That is a statistically very meaningful overdensity, and it is aptly named the Leo overdensity because it's towards the constellation Leo. And this has been a bit of a mystery in the hypervelocity star community for the last however many years. So several sort of ideas have been put forth to explain this overdensity, some of them including a dwarf galaxy that is disrupting, but not really detecting anything else but these hypervelocity stars, and also those invoking the LMC. Somehow the LMC is maybe producing these overdensity of stars. So we wanted to revisit that idea. And the reason for revisiting is that there's this bit of a renaissance in the effect of the LMC on the Milky Way galaxy, right? So if you ask someone 20 years ago, what is the mass of the LMC, they would have either said, we don't know, or very light. Nowadays, we think the LMC is actually very massive, and it also leaves behind very predictable and very falsifiable effects on the overall halo as well, such as this one. So This is a very recent model of the LMC from Nico Garvito Camargo in 2019, and it predicted these overdensity of halo density, of stellar density in the halo that was later confirmed and detected by our own Charlie Conroy here. So just in light of all these new things that we know about the LMC, we wanted to see how that affects the origin of these hypervelocity stars. So if there's one thing that I've learned, it is to not do a live demo. So here's a live demo during a talk. The problem that we are investigating is quite simple. It is, we know from simulations what the LMC orbit down here is. We know what the Milky Way's orbit is. So we're just kind of integrating this orbit back in time by setting time equals negative, and then seeing where this blue massive main sequence star goes through. So in this one, particularly, it goes through, come on, ooh, it goes right near this central black sphere, which is the black hole. So then we can record the positions of these stars and how close they impact the Milky Way center, and make it as a nice 3D histogram. So for this particular star, HVS4, sampled from its observational uncertainties, it goes bang on through the middle of the galaxy, as you would expect from the Hill's mechanism. You do that for another star, HVS7. Again, the same kind of star, hypervelocity, main sequence, blue main sequence, all that. And this one never even comes close to the galactic center. In fact, it's about 20 kbc offset from the galaxy at its closest passage. But it goes through the LMC. Isn't that curious? So if you do this analysis for all 21 stars, this is what we end up with. The red stars, colored over there, track back to the LMC, but not the Milky Way. The black stars track back to the Milky Way center, but not the LMC. And then the purple stars, we're not exactly sure where. We need a little better data. But I noticed two things. First of which is there's a lot of red points. About half of them come from or track back to the LMC. And then second, the ones that come from the LMC are all in one part of the sky, which is exactly where the LU overdensity is. So maybe it actually can explain the LU overdensity. So the obvious thing to do now is to ask the question, well, if there were actually a supermassive black hole in the LMC, what would it do? Here's another. So now we're doing the reverse or forward time model, where we model a supermassive black hole in the LMC. It is allowed to produce hypervelocity stars at whatever rate it likes to. And then these points are now colored by the velocity with respect to the galaxy. So this is the actual number that would be going to the selection criteria. And as you can see, there's a bit of an overdensity of hypervelocity stars leading ahead of the LMC, but not behind it. And that's precisely because the LMC is moving too. It's moving at 300 kilometers a second. So whatever star is produced from the galactic center of it, it'll only gain an additional boost if it's ejected in the direction of the LMC. If it's produced in the backwards, it doesn't get any boost. And then it basically is a normal blue star that has no excessive velocity in the halo. So at present day, what this manifests as is, from the galaxy, check this out, an overdensity of hypervelocity stars in one part of the sky, like right there. So back in 2D, this is what it looks like. This is, again, the same galactic sky that we're looking at. The black points are where the hypervelocity star surveys are. The red contour is a model prediction of where this overdensity should lie. And then it lies basically right on top of the observed overdensity. Oh, I love that chord. So just to put it side by side, left side is data, right side is model. In the case of a supermassive black hole, you can really reproduce it very, very nicely. If you invoke some other processes that involve the LMC disk, if there's star formation in the LMC disk producing supernova runaways, you don't get this overdensity because the disk is rotating, and that imparts a sort of tangential velocity spread. Of course, the Milky Way is also forming supernovae and star formation as well. Those also do contribute to the hypervelocity star survey sample, but they do not produce this known overdensity at all. So, oh yeah, this is just to emphasize again, the only way to reproduce the low overdensity is with a central supermassive black hole in the LMC. So using all that, we can actually constrain the mass of the LMC supermassive black hole as well, which my tongue is telling me just call LMC star. So by modeling the ejection velocities and the number of hypervelocity stars from the LMC, we constrained the mass of the supermassive black hole to be 6 times 10 to the 5. And this is a very well-known relation called the M-sigma relation, where the central velocity dispersion of stars and the mass of the supermassive black hole are tightly correlated. Blue line is for the general field galaxies. The magenta line is for specifically dwarf galaxies. And you can see that our estimate for the LMC supermassive black hole lies exactly on top of both. So it is fully within our reasonable expectations for the mass. So I'd like to conclude with this one sentence again, right? The discovery of even one such hypervelocity star will be compelling evidence for a supermassive black hole. How about 10? So with that, welcome to our next near supermassive black hole. Thank you.
There is one point that you didn't emphasize, and that is the location of those stars depends on the duration of the journey. If you wait long, I mean, the LMC is 50 kiloparsecs away from the center of the Milky Way. So if it shoots off stars, where they appear in our sky depends on how long the journey took, or what is the speed of those. And so you must have included something about the ages of the stars.
Oh, yes, absolutely. So if you look carefully, the stars actually are evolving on the HR diagram on this plot. So if the stars are too old and they evolve off the main sequence, they die in this plot. So all that effect is included.
Right, but the velocity also affects how far they go.
Yes, absolutely.
So what was the velocity that you assumed?
Oh, we don't assume it. We produce it self-consistently from the Hill's mechanism. So given a supermassive black hole mass and given properties of the binary, there's a prediction for the distribution of velocities produced from the black hole. That's the velocity that we've used. And in the end, you only end up selecting things that were born at 600 kilometers a second or above. But yeah, that is an artifact of the selection function.
Okay, and there are other big galaxies that merge with the Milky Way, such as the Sagittarius dwarf galaxy, many galaxies in the history that are not less massive.
But these stars are maximally like 200, 300 million years old. For Sagittarius A star to have imparted this 5 giga years ago, the stars would just not be alive at present day. I'm sure there are such stars, but they wouldn't make it into the main sequence blue massive young star catalog. They would be sort of field halo stars at this point.
And the star formation rate at the core of the large Magellanic clouds is consistent with how many young stars?
Oh, we actually don't know. We haven't found a nuclear star cluster in the LMC yet, so it is poorly constrained. So there's no number that we can actually just compare it to, let's say. Dozens of them, there we go.
Sorry?
There are dozens of star clusters close to the center. You don't know which one is nuclear.
Exactly.
Sorry, why?
In the Milky Way, in the LMC, there are dozens of star clusters in the region that is close to its geometric center. And you cannot really assign which one is the nuclear.
Because we don't know what the nucleus is.
Because we don't know if there is a nuclear star cluster, if it has been formed at all in the LMC.
Well, now we know if these stars are,
That's right, yeah.
So maybe connecting the dots would be useful. Yeah.
Absolutely.
Other comments, questions?
Yeah, I would comment on this, that there's a large and completely unexplored data set on the LMC that is 1,000 Muse pointings covering in 1 square degree of the center of the LMC.
Right, yes.
And no one has looked at it in detail.
So
it's GTO program, so nobody cares about it.
I think someone has tried to measure a kinematic mass of the black hole from there, but the upper limit is like 10 to the 7.
10 to the 7.
Yeah, exactly.
Yeah, because the average velocities in every pointing, instead of
Yeah.
looking carefully at like 10,000 stars that they covered, they would just average everything and extract the radial velocity. This was Vandermar's paper.
Yeah, absolutely. I agree. Yeah.
Why don't we see this black hole? I mean, it must be very dormant if it's there.
So, if you assume Sagittarius A star X-ray luminosity and radial luminosity, it should be visible. Again, it goes to the question of, we don't know where the LMC center is.
No, but we should see the radio source.
Yes, and there are several point radio sources that are also X-ray sources in the center. So this is motivating an observational search to go and find it, but the reason why we haven't found it yet is because, one, there hasn't been an evidence for a supermassive black hole in the LMC, and two, you don't know where to search yet.
So there are sources with the same spectrum as Sagittarius star?
Not the same spectrum per se.
Because we would expect it's similar in mass.
Yeah. These are all phenomenal questions, and the Same questions I'll be investigating in my
Yeah, but what's
postdoctoral
the
thesis.
answer? Other sources like Sagittarius A star.
Yes, yes, there are.
But
There are.
the point is that you don't know if these X-ray radio sources have flat spectra like you'd expect, right?
Yeah,
You
yeah,
don't
that's
have those data yet.
Yeah, exactly. That data is being taken very, very soon. So, again, obviously, this is a very unexplored territory so far, which is why I don't have the answers. But
Okay, that's surprising because LMC is very close to us.
It's in the south and astronomers are in the north.
Okay, any other questions? Yes.
So you mentioned that the velocity is affected by the mass of the black hole. Can you reverse that and do something about the properties of the black hole from the hypervelocity stars, or is it degenerate with the binary parameters?
no, that's exactly what we've done here. We've marginalized over all the binary properties to obtain an estimate on the black hole mass. Yeah. So I didn't show you the corner plot because
So
corner
this
plots
is
are
not
black.
from the scaling relation. This is independent of the scaling.
This is independent. This is what falls out of our Hill's mechanism analysis.
Okay. Is there a question? Oh, okay. Let's thank Jesse again.
Whose VLT was data you're talking about?
It's in the archive, it's the GTO program from Potsdam. From Potsdam. From Potsdam, I don't remember, somebody from Potsdam. I mean, I can show this to you, just open that.
Well, so what set this off, this talk, is that I was working on my ORCID site, and I noticed that there was this paper which I wrote a half a century ago, which is still cited. And it still gets several citations a year. And so I thought I would talk about it, and perhaps there are some, I mean, like everyone, it would be nice to have all of my talks be cited 50 years in the future. And this is what the ingredients are. So here's the paper. It's my first sole author paper. I had actually written, I had participated in a couple of papers previously, so these are kind of lab and observational work pieces that I'd gotten a part of. But this was my first solo paper, and it was the result of interaction with these two guys with famous names. So S. Chandrasekhar and Martin Schwarzschild, they are both professors. I was a first-year graduate student at Princeton, and these two guys were very good friends and saw each other very often and worked on similar things. If you look at what they worked on, there is a lot of commonality. For example, Emden, the uncle of Martin Schwarzschild, invented polytropes, and these were what Chandrasekhar did as his thesis. So a lot of commonality between these two. They were also both significantly shorter than average. So I recall actually being in the hallway at Peyton Hall with the two of them arguing about my project, and I went like, "Hey guys, I'm still up here." And of course, Martin Schwarzschild is the son of Karl Schwarzschild, arguably the greatest astronomer of the early 20th century, and the finder of the Schwarzschild solution for the Einstein field equations, and numerous other things, including observational instruments and lab techniques. So, and as I'm pointing out here, all of these guys, well, both of them have uncles who have craters on the moon named after him, and Schwarzschild also eventually got a very large crater on the far side of the moon named after him. Karl Schwarzschild served in the German army as an artillery officer during World War I. His wife and 3 children suffered through a lot of the turmoil of the 20th century. So his oldest daughter, Agatha, managed to emigrate to Great Britain. Great Britain had a program for having the Central European refugees. They would if they were academics, they'd send them off to these rural colleges in New Zealand, and so you often find that they're very high-powered academics working at tiny little colleges out in the boondocks of New Zealand, and Agatha was one of them. Alfred, the youngest son, remained in Nazi Germany and died in the Holocaust. Martin left Norway. He was in Oslo right after his PhD at Göttingen, and he got out of Norway just in time and came, in fact, to right here. He was a postdoc here at Harvard College Observatory. And he served in the U.S. Army Intelligence Services during World War II. This is what you get if you're a Nazi. Your own citizens wind up in war against you. And he was able to pass off as a German citizen because, of course, he was. And, he had a better war than Ian Fleming. So. He did his part. So how do I come into this? Well, Martin was assigned, I was assigned to Martin. At Princeton, the way they do the graduate student work is the first year you do 2 projects, and your second year you do 1 project, and then after that, you start your thesis. And the idea, which Lyman Spitzer originated, was that these assignments would be against the inclination of the student. So I had been doing these observational and instrumental things. And in fact, I had been designing a plasma diagnostics unit for Lawrence Livermore Lab, and I had been using the Princeton computer. And so my box of cards, of IBM cards, would go into the computer and they would come out, and it was labeled Stark, S-T-A-R-K. And just by coincidence, Martin Schwarzschild at the time had been working on, he had first done star A and then star B and then star C, and he had just gotten to star K. And the 2 boxes kept getting mixed up, and Lyman Spitzer thought this was very funny, and so assigned me to Martin Schwarzschild. And Martin was just an absolutely lovely person. I mean, he would come into a room and he'd light up the room. He was nice, he was kind to everyone, and he was generous, just the greatest guy. And his wife, Barbara, was also lovely. He was active participant in the modern culture in mid-century New York. He had a Mondrian, which he'd gotten directly from the artist. And if you went to dinner at his house, he would pull it out and he'd turn it and he'd say, "Which way does it go?" And you could always tell, actually, which is interesting because there was a scandal a couple of years ago where a Mondrian was shown upside down in a museum, and they should have known better. And then there's Chandrasekhar. Chandrasekhar, yes, he had this thing, he had taught a course in field theory at the University of Chicago that had only 2 students, which were T.D. Lee and Nanqing Yang. And those 2 guys went on a couple of years later to show that weak interactions violate parity conservation. And within the first 5 minutes of meeting him, he made it clear that I was not as smart as Yang and Lee. But I already knew that because I had actually been through the entire undergraduate physics program at Caltech, where one of my fellow students, and in fact my friend and a member of the same student house, was Joe Polchinski, if you know what that meant. So I had already had the stuffing knocked out of me, and being told that I wasn't as smart as Lee and Yang was not any surprise to me. But Chandrasekhar invented this project for me, which was what is going on with elliptical galaxies, and in particular, can you have an essentially symmetric galaxy which looks like there's an isophotal twist? This was kind of a big deal back then because the big new thing, there were still no real CCD images. They were just beginning to come online. But there were plate digitizers, and so you could take these old photographic plates and digitize them, and one thing you could do with such a thing, with such a data set, would be to find the isophotes. And people found isophotes and found that they, in fact, sometimes rotated. So the inner isophotes would be at a different position angle on the sky than the outer isotopes of the same galaxy. And the question is, why would that happen? And here's an example of that kind of thing. And Chandrasekhar wanted me to investigate that and to show, in fact, what he told me was that if you had a symmetric galaxy, that there are ways of looking at it where this would, in fact, be the case. And I eventually proved that that was not true. It took me perhaps a couple of months in order to figure out that he had actually got it wrong. And so this is the kind of thing, and the result was my paper. So I should mention a homioid is a shell bounded by 2 identically oriented ellipsoids. That is one of these wonderful geometry words like frustum, where you have a very specific short word for a kind of weird thing in geometry. And the interesting thing is that any line through a homioid results in 2 line segments, and those 2 line segments are always equal. And I did not know this going in. I wound up discovering it for myself. I'm certainly not the discoverer of it. Certainly, in retrospect, it's pretty clear that Isaac Newton knew this. So it wasn't, I may have discovered it independently, but this is, however, what resulted in the symmetry which caused the whole problem to come apart. And I produced this proof, which, if you really care, you can look it up in the archive. And so I eventually wound up setting up the problem using the mathematical machinery that they taught me at Caltech. You have the Euler angles and you have analytic geometry, and then you just figure out what the lines of sight are doing and you integrate. And that trick with the 2 identical line segments allows you to simplify everything and show, in fact, that these things are true, that in fact in an absorption-free stellar system, the isophotes on the sky are basically going to be the projection of the homeoids, which are the volumes of constant volume brightness. So it just does the simplest possible thing. It just projects as you might think, which is the opposite of what Chandrasekhar had told me. So one thing this allows you to do is this kind of thing where you can, if you know the angles, and perhaps you can determine that by velocity measurements or other means, you can figure out what a triaxial model of the galaxy actually is. I point out that this result here, this is actually the high school trigonometric problem from hell. This thing winds up blowing up into about 150 terms that are quartic and quadratic and sine and cosine of the angles, and it's just a monster to solve. But I will here do the dreaded demonstration, which of course doesn't work. Yes, so this is Maxima actually doing that. And that was not available at the time. This was a program that was developed some years later. Now it's free because it's such an old program. But the whole monster deal can be done by machine. And I think one of the morals is that you've got to stay ahead of the computers if your paper is going to be referenced 50 years in the future.
You may not remember it, but when I started astrophysics 37 years ago, I remember you at the IAS luncheons, which were a version of what we have here right now. And you were very prominent, speaking a lot there.
But mostly about instrumentation.
Yes, that's right. And the other thing is, when I arrived at Harvard, George Rybicki from Rybicki and Lightman, he was working on a paper about the inversion of triaxial systems, and one of the things he proved mathematically is that it's not unique. In other words, you can have multiple sources that give you the same outcome when projected on the sky. So there is a paper by George, actually more than one, on that. You might want to check it out. He did a very interesting...
Well, it's a little late to ask him to reference my paper.
He did. I would guess he did.
But if you look at the details in the math, it's clear that, well, the solution is unique if you know the three angles. And if you don't know the three angles, then it's totally a three-parameter system. If you know that, like, the central bulge of a galaxy, if you know where the plane of it is, then you kind of know two angles, and then there's only one angle of ambiguity left.
Any comments or questions to Tony about the last 50 years?
Yeah, I'll comment again. Maybe you said that Chandrasekhar thought that the isophodal twist would be caused by the triaxiality. So he was not really too far from the truth, because as it turns out, the isovelocity twist in the kinematics of a triaxial galaxy can be explained by triaxiality alone, without involving embedded disks. And this was like a big thing at the late 90s, when people started to find to discover elliptical galaxies with minor axis rotation. So basically, the outer part would have minor axis rotation for an elliptical, but the inner part would be like looking like a kinematically decoupled core. And I think it was Tim Dessou's paper in 2002, one of the first papers originating from the Sauron survey, where he showed that for one of such galaxies, this can be just explained by the orbital superposition using Schwarzschild method. And this is that Schwarzer that you're mentioning. as
Yes,
far as I understand.
yes, so-
It's not the father, it's the
But
son.
the-
Yeah.
But that, Schwarzschild did not start on all of that additional kinematic stuff until after my paper, right? This was the very first paper, and over the years, actually, I've had people come up to me and go like, "You're Stark, you're the founder of my field, and you're still alive?" So, yeah, a lot of people have done a lot of good work on this, and the kinematics is important, but this was the first and last thing I ever did on it, and in fact, it pretty much convinced me that I didn't want to be a theorist.
You're still welcome at the ITC if you change your mind. Any other comments? If not, let's thank all our three speakers.
Oh yeah, that's